Thank you. Okay, can I? Okay, okay, sorry. So CA2 cover from week 1 to week 3 is altogether 33 points. 33 points. Okay, and as I said, if you have finished all these interactive questions, you get 5 points already. Okay, which means in next week's quiz, I'm only test you 28 points questions. Sorry, this mouse cannot work right well, so you have to follow me. Otherwise, you don't know what I'm just writing here. Okay, so this is CA2. So for CA3, so you have 2 portions. So 17 points is coming from Prof. Eugene's part. So you have to ask him. Someone ask questions. Yes. Next week and next Tuesday. Okay, so Eugene's part, you have to ask him what he is going to cover in his part. So in my part, 17 points only covers weeks 4 and 5. So which means what I tested next week will not be tested again in the last week. So it clear? Is it clear? Okay, can you give me some? Okay, it's very important now. Okay, so which means because our my part is in the last part, second part, so it's a bit weird for me if I test again for what I already tested in CA2. Okay, so 17 points for me. So it's week 4 and 5. Week 4 and 5 only. Okay, so so that's the most important thing. Okay, and also the other thing you have to keep saying is don't skip any of these CAs. Because no matter what, even if you're under quarantine, we still have to give you makeup. Even you have MC, you still need, no matter what, you need to have a mask. Okay? This is a school new policy. Not like before, you can have MC, then the marks can be proportional, but not this, starting from this year. Clear? Clear? Okay. So let me move on. Again, emphasize C2. Okay, cover week 1 to week 3, okay, until today, basically. And also 5 points was already given to you if you have finished the LAMPS sequence, okay? And the CA3, which only cover last 2 weeks. So last 2 weeks, week 4 and 5, okay? And also Eugene's part also is going to have another half, but what content he need to test you, please double confirm with Prof. Yu. Clear? Okay, my part is very simple. Next one, CA2, week 1 to 3. CA3, 4 and 5. Okay, clear. Just one last message. Don't skip it. There's no point. Okay. What are the operations, turning, milling, and drilling, and the machine that can be used for feature 1 to 4? Okay, so you can see, so 1, I just make this one become smaller, diameter becomes smaller, and the 2, which is make this flat surface, and all this drill a hole here, and cut off to form this start from 200 millimeter to 150. Okay, so let's quickly review what we have learned. The outline for this whole course, machine introduction, so traditional materials removal. So we've very much focused on, actually we very much only focus on turning, okay, but turning, drilling, and milling is one of the very common one here. So all these basic components of machining is the cutting tools, tool knife and well, and also failures, and also cutting tool materials. Okay, and the last portion is non-traditional. So we have 4 type non-traditional ways, and water jet way and the EDM way. Okay, actually it's very straightforward. So for the section 1, so we talk about the machining is a subtractive way, and there's 3 major types. So the conventional ones such as turning, drilling, and milling. Okay, but there's also a non-traditional one, so which is mechanical, electrical, thermal, and chemical. So we learn EDM. We also learn water jet, right? Water jet is this mechanical. Okay. With the jet, okay. A basic one is not required, but actually it's very much used in like semiconductor. They use this polishing to make your wafer very, very smooth, very, very normal. And also in most of this machining, you have 2 motions. One is primary motion, and the second one is the secondary motion. So this two things. Either is your work with the workpiece is rotate or your tool is rotate. Okay, so this one is going to help you to form certain shapes. The advantage of machine is the most important of machine, why people use it almost as a last step in all the process. Okay, because they can give you very high dimensional accuracies. So if you're done this impact question, for the first question, I say, hey, can this be done by casting? I expect all of you say no, because casting is definitely not the one give you the very high dimensional accuracies, okay, and good surface and complicated shapes, okay. So normally the machining give you the best possible dimensional accuracies. The disadvantage, you have to cut away a lot of materials, and that's high cost and time consuming. Most of the time you can just maybe, if you drill things or turning things away just one by one, right? So that's why. So our aim, number one thing is always with accurate dimensions and try to get smooth surface finish and high speed and low cost. Okay, so continue. Okay, so you can see we talk about turning, drilling, okay, and the milling. Turning to the milling. Okay, so basically it's just how this tool moves. Like in this, turning is a move, works in this way, actual way, and drilling is moving down and also at the same time rotate. And the milling, it is also rotating, because it is rotating and moving, okay? So the workpiece rotates, drill, tool rotate, and the milling, which is tool rotate also. Okay, so the feet could be either parallel or perpendicular. So all these please just figure out by yourself, okay? You just need to remember all these movies, then you can answer all these questions very easily. We have seen a lot of movies, right? So the mysterious operations on lathe, so we say the big thing is like turning. So in turning, you can either get the straight turning, okay, or taper. So get this taper shape, okay, or the round shape, conical shape, round shape, okay, profiling, and also the grooved one. All sorts of things can be done. And the facing, facing means now, because in this case, right, in the turning, so the tool moves this way, which is perpendicular to the axis of this whole workpiece. Okay, so these two are parallel, but in this case it is perpendicular. Okay, the axis is this way, but the tool works in a perpendicular way. Okay, but in this case it is parallel. This is grooving. Okay, so what they do is produce a flat surface at the end of the part, or you give them a face movement. And the cutting with a form tool, so which means now you have a tool form. Okay, so you are going to replicate this tool form into your workpiece. Okay, and the boring, a name is very well, right? In a notch, a hole or cylinder cavities to produce internal grooves. Just enlarge the holes or cylinder cavities or produce the internal grooves. So the drilling, so what we said before, drilling can be done on the drill process, but also in this case can also be done on a lathe. Okay, if the drilling is like this, okay, can also be done. And the parting is mean get rid of everything. Get rid of it. Okay, and the thread is to produce external or internal thread. This thread. Okay, and the learning is going to give you like what you have seen like in the knob and handles, right? Give a little bit friction, easier for you to turn. Okay, so these are the 7 quite standard and common operations on a lathe. Okay, there are more. I just summarize a few here. Okay. So go back to our question. So first one is what? Tell me, first one. Can you write down your answer? First one. Turning, correct. How about second one? This one is what? Excellent. Third one. Third one easy like drill. Have to be drill. 4. Anyway, okay. So the first one. Yeah, parting, part of turning. Okay, part of turning. Okay, but they have names for it, which means it's parting. Okay, parting means get rid of it. Cut off from 200 millimeter to 150 meter. Okay, so make it shorter. Okay, so the turning is going to be done on the lathe. Milling is on a milling machine. You make some like flat surface. drilling is very often used in the drill press, but also can be done on the lathe. Okay, and the parting, parting is going to be on the lathe. Okay, parting means cut away this. Okay, okay. So this is the first one, the operation. Okay, and draw a schematic diagram to show the formation of chip using a sharp cutting tool in turning. Okay, label the diagram accordingly. Okay, actually you have learned this, right? So we just simply copy. Okay, but it's pretty important here. Okay, so the cutting, you can see where's the tool. The tool is this gray one, right? The tool is this one. Okay, and this is workpiece. This workpiece. So this one is tool. So the tool have two faces. So two faces. Okay, so for example, this face we call it a rig face, which is in connecting with this chip, and there's a flat face which is closer to the workpiece. Okay, so unfortunately, all these are terminologies you have to remember. Okay, this is a characteristic of this course. There's too many things you need to remember. Okay, but if you go to industry, you don't know this, you just make a fool there, right? So just try your best to learn it. Okay, to remember it. So we have cutting tool. So cutting tool. So simply just this line here. So you can imagine this whole thing. Okay, so it's behind it, cutting tool is separate the chip from the parent work and the materials. So basically the rig face, so this is a rig face, which is this face. And also the flat face is connecting with this one. In the end, right, you have something like this. So which means this is your cutting. Okay, so this is your cutting edge. Cutting edge. Okay, so this surface is your rig face, and this surface, the below one, this surface, it is your flat face. Flat face. Okay, rig face and flat face. Okay, so then these two faces is connecting, intersecting at this cutting edge. Okay, so the cutting edge, which is used to separate the chip from the parent work, and the rig face is going to direct the flow of the newly formed chips away. And the flag, which is going to provide the clearance. So you can see there's a clearance here. Clearance here. Okay, so the clearance between the tool and the newly generated work face. So this is going to protect the face from the abrasions. Okay, so that is this diagram. Okay, the others maybe no need to know, like a shear plane, rough surface, and the shear angle, shining surface, no point. So all this is only mentioned here. So you need to remember, and also chips, of course you need to know where's the chips. Where's the chips? Okay. Okay, so that is the tool. Draw this diagram and show the formation of chip. Use a sharp edging tools in turning. Okay, so then this Taylor equation again. And this week, the calculation is super simple, too simple. Okay, so use the Taylor equation because all this we call this one, normally we call it an empirical equations. So normally are very easy. Okay, so use Taylor's equation for true life, n equals 0.5, c 120, calculate the percentage. So can someone give me your answer? Clarence, what's your answer? Have you done it at home? Jihao, Josephine, Junior, Hao Ying, Eugene. Okay, 400. Let me see. The question asked is increase a percent. So please read the question. Percentage increase. Okay, so let's see it together. Okay, first of all, use that equation. This is equation. Remember, this is a big V. Big V, which is a cutting speed. Okay, so later I'm going to say this again. Okay, cutting speed, and the T is time, is life. Okay, time, you can see it's a constant. So you simply just use these simple equations, V, T, N equals to C. So V is a cutting speed and T is tool life. Okay, so for the one, we have two different cutting speed. Okay, so the T1 and T2. So when the cutting speed reduced by 50, so which means now the V1 and the V2, the relationship will be half, right? Half. So, okay, so V2 is going to be the second, I mean, after the reduction, V2 is going to equals to 0.5 V1, okay? So we put everything in. So this is before you decrease the speed, V1 T1 0.5 equals to V2 T2 0.5, okay? So then you change this V2, use this equation. So then this V2 is going to equals to 0.5 V1. Okay, then you get rid of this V1 here. So in the end, you will have T1 0.5 equals to 0.5, T2 0.5. Then you put square on both sides. So in the end, you will have T2 equals to 4 T1. But my question, I think this is the only possible mistakes. That's why I asked your answers. Okay, this is the only possible mistakes you're going to have, which is the question I'm asking you is percentage increase. Percentage increase, which means you need the, okay, when every time we talk about percentage increase, we have to use the T2 minus T1 divided by the T1. Okay, so if you compare with anything, how can you say percentage increase? We compare with anything. So for example, you compare with A. How can I say I compare with A? What is the percentage increase? So it is always B minus A divided by A. Okay, so this one, it is percentage increase. This is only possible mistakes. Yes, thank you. Thank you. Okay, so will be 300. Okay, so with 4 T1 minus T1 divided by T1 will be 300. 300. Okay, so this is just some like more often used in industry and also academia. When every time people talk about percentage increase, you have to minus the benchmark and divide it by the benchmark. So in this case, the benchmark is before you decrease the cutting speed. Okay, thank you, thank you. Okay, so this is a third question. So, and of course now you can see if we reduce the speed, which means our cutting life is going to increase. But I'm asking you brainstorming questions. Please just input your thoughts here. Okay, it's not like a standard answer for you, but just please discuss it. So since we said true life can be almost infinite at low cutting speed. So would you then recommend that all cutting is done at low speed? Please input your thoughts here. Can you type your answer here? I mean, not even answer for this one. We just discuss. Okay. Can you input your thoughts here? Yes or no? If too slow? Oh, okay. This is actually a very important point. Okay. Yeah, Karen said, economic purpose, no customer can't wait. Everyone want first, correct? Okay, no produce. Yeah. Hey, Hao Ying also mentioned a very good point. Could produce poor surface finish. Excellent. Hao Ying, wow. Okay, very good, very good, very good. Okay, yeah, excellent. Time consuming, correct. Very good, very good. Okay, yeah. So as I said, this is just brainstorming and there's no like standard answer. I just suggest a few things. Okay, so true life can almost become infinite at very slow cutting speed. But owning this thing, you cannot justify. Okay, so since you join our school, you will be material scientist. You're already defined as material scientist. Okay, so the only thing you might learn after 4 years study or 3 years study here, you will know that in the end, it's all about choice. There's no perfect solution. Okay, there's no perfect solution. You always have to balance from so many different considerations and make the possible, best possible solutions for it. Okay, so there's no like definitely very good or very bad choice. Okay, so you have to justify. So that's what we said. But this reason alone does not necessarily justify using very low speed. Why? Okay, so student mentioned remove less materials in given time, which unless otherwise justified would be economically undesirable, right? So I mean, it's all about money. Come on, if you cut too slow, right, it's too expensive. And also, as the student Hao Ying suggested, that the lower cutting speed may also lead. This one actually I didn't mention in the notes, okay? But this again, happens. Lower cutting speed actually often give you the formation of built-up edge and discontinuous chip, and thus affecting the surface finish. So remember what is BUE? Do you still remember? We said there are 4 types of chips, right? Four type chips. So BOE is one of them. Discontinuous one is also one of them. Okay. So BOE, which means your chips is deposited on your tool. Deposited on your tool. Okay. So this is not nice because it's going to affect in the roughness and the surface finish. Okay. So this is just brainstorming. Okay. So then the question here is, so in actually most of the, almost all the chips you have to remove, right? So in order to remove it more effectively, what ways you can use to remove all these chips? So I think we mentioned one in the class. Can you keep thinking what I mentioned in the class? How can we get rid of the chip more easily? The chips, because the chips, if stay there forever, won't disappear, then it's definitely is going to influence the surface and also, yeah, very good. Thank you, Yi Qing. Thank you, Yi Qing. Chip breaker, chip breaker. Okay. The last session, one more student mentioned about one thing I didn't think. CA2, how many questions? Oh, can we answer this question later? Okay. Yeah, okay. So in the last question, last session, one more student asked, what are there's another way like I use fruit to fart away, okay, to brush away or use like gas. Yeah, all these are possible. Okay, so the general thing is please get rid of the chips. Okay, don't let chips stay there forever. Okay, so that is the question 4. Okay, and also a set of workpiece were turned on a lathe machine at a spindle speed of 150 RPM to reduce the diameter too. So which means this is DF, this is this is D no, which is beginning, DF is final. So in this is N, big N, okay, and the feed rate, which stays, the lifetime of this will found to be 200 hours. So if we increase to 200 RPM, so calculate the true life and also the MRR. Okay, so let's continue. So this one, it is very, very, very important. Okay, so you can see the materials removal rate. Okay, so for example, this one is a turning, right? Turning. So the first thing is this workpiece is turning. Okay, so turn at this N. So N is rotational speed of the workpiece, which is RPM, which means in 1 minute. So how many round revolution? Okay, how many round of this workpiece is going to turn? Okay, so this is first one. So the feet which is in 1 round. For example, if my workpiece turn 1 round, how far will this tool move forward? How far will this tool? So workpiece turn 1 round, how far will this tool move forward? Okay, so that is F, small f. So it's supposed to be here, right? So feet, you can see the feet here. Okay, starting from here to here. So this is feed rate, which means 1 round. So how far will this tool move forward? Okay, then if I need to know in 1 minute, how far will this move? So what will I need to do? I need to use this F. This is for 1 round, right? Times how many rounds? Okay, so this is small v, small v, which means some people call it a linear speed of the tool along the workpiece length. Some people call, because this is axis of this workpiece, some people call it actual speed, because this is the axis of this workpiece, because you rotate with this axis. Okay. So then there's another one, this small v, there's a big V, the big V. The big V now I'm asking you is, first of all, for this workpiece, right, for this tool, for 1 round, so how far it has been traveled relative to this workpiece? Did you get my question? So in 1 round, where this workpiece and also the tool move relatively, what's the distance? So you can see one round, the workpiece moved one round. So the tool actually relatively moved this circumference. Am I correct? Circumference of this length. Okay, so which is supposed to be pi d average. Normally we always talk about average. Okay, so pi d. So which is circumference of one round. But my question here now is in 1 minute. In 1 minute, will this tool relatively removed how many lengths of this workpiece? Okay, it means just travel how far already. So actually you still need times and n, right? So pi d is 1 round, you times n, which is for 1 minute, for 1 minute. So this surface has been traveled for how fast, for how far, okay? So this is big V. Then you have d naught, that's a simple one. The d naught, okay, d naught is here, starting, which means original diameter, and df, which is here. Okay, d average, you just d naught plus df divided by 2. The depth equals to d naught minus df divided by 2. Depth is this one. This is the depth. Okay, the time is easy, right? Time, the cutting time, because if you know the length of the workpiece, so and also you already know the V here, which V means you have to move from this end to this end, right? So simply just use L divided by V. This requires a width or linear speed of the tool around this workpiece length. Okay, so I think the only tricky thing here is this MRR. MRR is a turning, is volume of the materials removed per unit time. Okay, so now let's see. So you can see, right, for 1 round, now let's see for one round. So how many volumes? So how many volumes of these materials has been removed? In 1 round, I'm only talking about 1 round. I just, it's too messy here already. Yeah, you get my point? 1 round, what's the volume? What's the volume of the material you're going to get removed? Okay, so first of all, right, so you can see, so this one is moving this way, and also this is turning, okay. So first, they are going to remove a more or less like a ring here, this whole ring, which means is this whole ring, it is going to get removed. Am I correct? I'm only talking about 1 round, right? For round. Okay, you can imagine now if I turn 1 round, okay, so what's the volume of this whole thing is going to get removed? So first of all, so you need to know the cross section of this one, right? So this cross section, okay, the cross section is here. So cross section is going to be D times, this is D times F. Yes, D times F, D times F, okay? So that's the cross section. So the D times F is going to be the cross section, okay? So which means you're going to produce a ring, this ring, right? So which is D and F. For 1 round, so what is the length here? Oh, sorry. What is the length here? Tell me.
Circumference.
Yeah, very good. The circumference, correct. Okay, so this length is supposed to be the circumference. Okay, good, very good. So that's what we put here. Okay, because it's a bit messy. Okay, so for each revolution, for each round, a ring-shaped layer of the material is removed with cross-sectional area. First of all, is D times F. F is the fit times the depth, right? Then, of course, we know for 1 round, you are going to remove the average, which is average circumference of the ring, which is pi d, right? So that is going to be the volume you have already been removed for 1 round. Then my question is, in 1 minute, you're going to remove how many volumes? So you simply just need times the n here. Okay, so that's the MRR. Okay, so if you see very clearly, everything is very explainable. So it's just all these things. If I examine you, I'm going to give you the table, so no worry. Okay. Okay. So let's continue. A set of 31 millimeter diameters, which means this now is a DF. Dino, right? This starting Dino at the very beginning. Okay, this big N set. This is big N or small n, according to the table. Big N, right? To reduce to diameter to 30, which means this one's DF. So in one operation at feed rate, the feed rate, which is 30 millimeter per minute. So what is this feed rate? Can you tell me? Check the table. So this feed rate is what? Feed rate. Feed rate is where? Feed rate is this one. Feed rate is this. Small v, small v. Okay, so small v. And the life of the machine was found to be 200 hours. So now if I increase the spindle to 200 RPM, so keep all the other parameters unchanged, answer questions. Okay, the first one is very easy, right? This one very easy. Okay, so the thing is in the Taylor life, okay, so you have to use, it's not the small v, you need to use the big V to calculate. Okay, big V, which is surface speed of the workpiece in 1 minute. How far this surface, the tools moved this workpiece. Okay, so that's what we put here. So we need to use a big V. Big V, not small v. Don't confuse. Okay, big V, and the V1, the V2 speed is for turning operation. So of course we know that so V is equals to pi d average times n. Pi d average times n. Okay. So continue. So D average will be 30 plus 31 equals to 30.5. Okay, so V1 is going to be pi D times N1. Okay, and this one is also pi D times N2, 200 millimeter per minute. Okay, so then we already also know that T1 is equals to 200 hours, right? 200 hours. Okay, this one was given already. So actually, you just need to calculate this T2. Okay, because it's equal to constant. Okay, so we put all the value in. This is the average. This is N1. This is T1. This is average D. This is N2, right? Because we increase to 200 RPM, and we need to calculate this T2. So put all the things in. You can get rid of all this. So actually, it's very straightforward. T over 200 equals to 100 to this 200. Okay, so after calculation, is reduced to 173 hours. Okay, so this is simple question. Simple questions. Do you have question? Okay. Yes. Oh yeah, circumference correct. Okay. So let's continue and let's continue. Okay. So now let's calculate the MRR. So the MRR. So we can actually do a little bit of this MRR, the variation here. Okay. So from this question, the table we know which is pi d dfn, right? Pi d dfn. So what is fn? Can you go back to check your table? What is fn? Can someone type? Big V or small v? Karen's? Small. Yeah, it is the smaller v, okay? Okay, so which is supposed to be this one, 30 millimeter, okay? So this question can also, equations can also be changed to pi d small v, okay? Because we know that Fn is also equals to the feed rate, okay? All sorts of variations, okay? But doesn't matter, okay? So then the materials removal rate, which will be pi d average. D is smaller d is the depth of cut, okay? And the big D, the feed rate, then simply just this is 30 millimeter. Okay. Okay, so that is all. So we can, the final answer is going to be this. Okay, so it is pretty straightforward. Okay, so that is a take-home point. So we have learned, okay, turning, drilling, and milling have different cutting edge. The relative motion between the workpiece and tool are different. Okay, and also we have learned 7 different big categories of operations on a lathe. Okay, the tool, the turning tools are please remember all this like wake, what are the wake, what are the flank, what are the chips, okay, all these are very often used. People talk about all day if you work in industry. So continuous, BUE, related, discontinuous, all these are chips. So all these chips are good and bad, okay, so but in general, in principle, please take away all of them. Don't just leave it stay on your surface. That's very bad. Okay, so you can use a chip breaker. You design a chip breaker to remove the chips. Okay, and also when we talk about wear, we have tool wear, including crater wear and flat wear, and also we use a Taylor equation to predict tool life. Okay, so tool materials. So you have high hot hardness, chemical stability, high yield strength, and high stiffness. And since we said we don't like the surface become too hot, so you have fluid to have a few things. Number one, you can use as a coolant, right? Coolant, and also you can reduce the friction. And but this have problems. Okay, this method have problems because you're going to cause a lot of environmental pollution. That's number one, and also it's costly, right? You need to use fruit to remove, so it could be very expensive. So that's why nowadays there are some new trend in this whole industry. People use near dry, and also cryogenetic way, okay, to act as a coolant and reduce friction functionalities. Okay. And also last one, I think the last section is so simple, right? So I saw it's too simple, so there's not much you can talk. Okay, explain the work principle of EDM. So what is the possible surface damage? So first of all, what is the EDM? So EDM, we say, okay, the keywords, discrete electrical discharge. So basically just a spark. So this spark is going to have very high temperature and can melt or vaporize the metal in this the vicinities of the discharge. Okay, so if you see a little bit more carefully here, you can see. So then this one, it is workpiece. This is workpiece, and this is tool. Okay, so both are connected with the electrode. Okay, so which means then you are going to have a high potential in between, right? High potential between, you can see. So both of them, the removable electrode also connected with current. So this one also connected with current. Okay, so all these things, then once its potential is high enough, potential between the tool and the workpiece is high enough, then you're going to have this, we call it a dielectric breakdown. So this dielectric breakdown, then you're going to have this spark discharge. The spark discharge is high temperature. It's going to remove, I think it's better you use that melt or evaporate. Melt or evaporate. I think if in the answer, I better change to evaporate or melt away a small amount of this one. You can see all these things is going to get melted. Okay, simple, right? Is it simple? Actually, the whole section here is pretty simple. And also, what is the function of the dielectric fluid here? So can, number one, act as insulator between the workpiece and also the tool. And this can also at the same time provide as cooling media, and also can even use as a flush. You can just flush debris in between the gap. Okay, so that is MRR. We didn't really talk about it. Okay, and okay, so that is answer. Okay, so maybe later when I provide the answer, I change this remove to a more like precise word, at this melt or evaporate. So when the potential between the tool and the workpiece is high enough, so dielectric breakdown and the transition spark discharge, you will cause this transition spark discharge through this fluid, and this one is going to have high temperature, melt or evaporate the small amount of metal away. Okay, the issue is okay, because in this case you have to use melting, right? So obviously you're going to have very high temperature. So the thermal effect is also called the material to develop heat effective zone. So this is heat effect zone. So this heat effect zone is going to change the hardness and ductility. Okay, so this is actually from last year's tutorial passed down by the previous lecture, but you just remember all these keywords. Okay, so what's the problem with the heat effect zone? Okay, so number one, it may cause recrystallization. So in this case, okay, so the grain most likely is going to become bigger. Grain will grow in bigger. This is a little bit more or less like a leaning, right? A leaning. You must have learned in other courses. Okay, if the grains is under higher temperature, so the grain normally will become bigger, the grain grows, and then this region will become softer and have lower strengths, because in most cases, bigger grains is going to have smaller, lower strengths, okay, and softer. Okay, so that's what we put here. So these are the keywords here. So that's the presence of heat affected zones where we weaken the mechanical integrities and of the metals. Okay. So that is question 6. Question 6. Okay, I think this week actually is very simple for me. I think this. If you next year will see me again, I'm teaching year 3 another course. There's so many math manipulation there. Okay, so for this course, you have to memorize. As I said, unfortunately, yes, some students ask questions. Yeah. I'm also teaching 3011. There's so many equations there. Yeah, a lot of math manipulation, but this course nearly 0, not much, okay, because, yeah, anyway, so non-conventional, we have thermal, chemical, mechanical, and electrochemical, okay, so water jet is actually this one, okay, EDM, it is actually this one. Okay, okay, so water jet actually use high pressure, speed, and water jet to cut surface. So some people still use a little bit like a basic powders like a silicon carbide and alumina to improve this MR, means can remove faster. Okay, the good thing for this water jet, since it's waterized, obviously there's no heat zone effects and the materials loss is minimum and not pollution because it's water again, easy to automate. But in this case, you cannot for glass because it's very easy to get cracked. Okay, so for EDM, EDM use a spark to vaporize the metal away. Okay, so we have dielectric fluids act as insulator, potential between the two become too high, dielectric breakdown and cause spark discharge. Okay, this is a full word, through the fluid, remove the materials. Okay, the thing is, so since we say you need to apply voltage on both tool and workpiece, so obviously only electrically conducting materials can get melted, am I correct? Okay, otherwise you cannot connect with the electrode. Okay, so that's one of the limitations, only the electrically conducting can work. Okay, and also since it's melting, you always have this heat effect zone, and it's expensive and it's slow. Okay, and the good thing, okay, compared with other machine methods, so it's can be used for very hard and strong, because this is nothing about mechanical anymore, right? So I'm used heat up, melt. So no matter how hard you are, so if you can get melted, then that's good enough already. It's nothing to do with the mechanical properties of the material. So very hard and very strong materials can be used this way to cut. Okay, so that is a take-home points. Actually, I think for the last 2 section action take-home points, I didn't give it you in the just the answer, right? Don't worry. So you come to the tutorials, then otherwise you will never come to tutorial. I'm just joking. Okay, yeah, okay. So that is all for today. So I think the quiz, the CA2 is until here. So one student asked, let me go back the question. CA, how many questions, and is there MCQ or so okay, it's very much similar to the tutorial questions. Okay, I normally don't give the MCQ. It's for the your university student already. Most of the time we need to write the structured short answer questions. Okay, so that's all. So I stop recording.